Okay, I'm going to go through some problems from the practice exam for kinematics. I'm going to go through the ones where Mr. Brigar is getting shot out of a cannon as a circus clown. And this set of problems sometimes is challenging for people because we want to sort of think that we know stuff. For example, it says Mr. Brigar lands on the ground 35.32 meters away after 1.17 seconds. But that was only true for one launch. And as you change the angle of the launch, or if you were to change the height, that time isn't fixed. Every time you change the initial conditions of the launch, the height or the speed or the angle, you're going to change the amount of time that a projectile is in the air. So I'll go through this and you'll sort of see there are some things that stay the same and some things that change. And part of the challenge is that you have to reason your way through what things are going to be different and what things are not. So we'll start by just drawing Mr. Brigar as a projectile from a perfectly horizontal launch, which is the set of conditions for problems 5 and 6. And the cannon is 6.71 meters above the ground. Mr. Brigar travels a horizontal distance of 35.32 meters. And the amount of time it takes is 1.17 seconds. That's the given information. It's a perfectly horizontal launch, so we know whatever his initial velocity is does not have any up and down component. And then, so we'll follow our problem solving procedure here. I'm going to say that directly below Mr. Brigar, where he starts, is our origin 0, 0, and our up and to the right directions are going to be positive. And there aren't any quantities here that aren't aligned with our coordinate axes. So I'm going to go ahead and start listing variables. So in the horizontal dimension, he starts at position 0, lands at position 35.32. His initial speed is unknown. His final speed is unknown. His acceleration should be 0 since it's free fall. And the amount of time he's in the air is 1.17 seconds. And number 5 is asking, what was Mr. Brigar's initial perfectly horizontal velocity? And if we plug all this into the solver, we'll get that his velocity must have been 30.19 meters per second or thereabouts. And since there's no acceleration, we now know both of those velocities. So the x velocity isn't going to change. For this launch, then, we know that we know the full parameters of his horizontal motion from the time that he's launched to the time that he lands on the ground. So now let's look at the vertical components. In the vertical direction, he starts 6.71 meters above the ground. His final position is the ground. His initial vertical velocity we know is 0 because this is a perfectly horizontal launch. The later launches aren't, but this one is. His final vertical velocity is unknown. He'll be moving down, but we just don't know how quickly. And then his acceleration in the y dimension should be negative 10 meters per second squared. And he is in the air for 1.17 seconds again. So we know everything except his final velocity. So we put this into the solver and we get two numbers out. We get 11.6 and negative 11.6. That positive and negative indicates direction. So we have to ask ourselves before we can answer the question, is he going up or down right before he hits the ground? And the answer is down. So his vertical speed using that last kinematic equation is negative 11.6 meters per second. And then what we're trying to find here is his final velocity for question number 6. And his final velocity has both a horizontal and a vertical component. So I'll draw my axis, and we know that he's moving down and to the right. His rightward speed, we calculated earlier, is 30.19 meters per second. His downward speed is 11.6 meters per second. And we can put that into the vector solver to determine that his final overall speed is 32.34 meters per second at a 21-degree angle. And that angle is below the positive x-axis. So we could say down and to the right. Okay. So then there's another launch. And in the second launch, it's the same cannon and the same base, but now it's set at an angle of 22 degrees. So if we take a look at what happens then, we get a different launch. So now Mr. Brigar is launched at a 22-degree angle, still going to follow a parabolic path. And what we want to do is launch Mr. Brigar through a ring of fire. And the ring of fire is set 13.17 meters away from the cannon. So there's a horizontal distance here of 13.78 meters. And then we want to launch him into a pool of freezing cold water. And the pool of freezing cold water has a rim that is 2.17 meters above the ground. And of course, he's launched at the same height of 6.71 meters. And the scale of my drawing is not great, but it's good enough. And we have three questions here. One is, where do we put the ring of fire vertically? The second is, how high off the ground will Mr. Brigar be at the highest point of his arc? That's not one that we solved in the lab, but it's something we can do. And the third thing is, if the pool of freezing cold water has a rim that is 2.17 meters above the ground, how far away from the cannon's base should it be placed so Mr. Brigar lands in the middle? So let's start with the ring of fire. Well, let's start by finishing up our problem solving system. So we'll say that 0, 0 is directly below the launcher. We have our positive directions being up and to the right. And in this case, we have a 22-degree angle to this initial velocity. The initial velocity is still going to be 30.19 meters per second, but that isn't the x dimension anymore. That is the overall speed, which means that at a 22-degree angle, the x part of that is going to be 28 meters per second, and the y part of it is going to be 11.3 meters per second. So the initial speed stays the same, but neither our x nor our y components of that velocity are the same because the launcher is now set to an angle. Okay, so now that's the only quantity that we need to think about in terms of breaking it down into vector components. So now let's go through and we'll just start with the ring of fire. So initially, Mr. Brigar starts at position 0 horizontally. He ends up at position 13.78 meters. His initial horizontal velocity is 28 meters per second. It's not 30.19 because not all of his speed is to the right. His final velocity is going to be the same because his acceleration should be 0. And we don't know how long that's going to take, but we have our kinematic solver that we can use. This is pretty straightforward. We put the numbers in that we've got, and then we're going to set the solver to tell us time by using that first equation. And we get about 0.49 seconds. So it's a half a second, but I'll just use 0.49 because it doesn't do any harm. And then for the vertical position of the ring of fire, we want to put it where Mr. Brigar is going to be vertically after he's gone 13.78 meters horizontally. So our initial position is 6.71 meters off the ground. Our final position is what we're trying to find. Our initial velocity in the y dimension, he's moving 11.3 meters per second upward. We don't know how fast he's going up or down as he moves through the hoop. His acceleration should be free fall, negative 10 meters per second squared, and the amount of time is going to be the same. So this is just like the lab, and we can again use that first equation to calculate the final position given all of this information, which I'm dutifully putting into the solver right now. And we know the time is 0.49 seconds. Trying to find final position, and it looks like it's about 11.05 meters. And this is a degree of precision that's ridiculous. You don't need to calculate it to this degree, but I did. All right, and then number 8 says, how high off the ground will Mr. Brugger be at the highest point of his arc? So we can just, that is only going to have to do with the vertical motion. And this is the same launch, so our initial position is the same, but we don't know how high off the ground he is. His initial velocity is 11.3 meters per second. His final velocity isn't given. The acceleration is negative 10 meters per second squared. And the amount of time, well, this is where this isn't the same amount of time that it takes to get to the hoop necessarily. I mean, maybe the hoop is the highest point, but we don't know for sure. So we don't know time. We don't know final position. We don't know final velocity. This looks like we can't solve it until we remember that at the highest point of projectile motion, an object will have a vertical velocity of 0. And as soon as we put that in, all of a sudden, we do have enough information to solve the problem. And in this case, we would use the third equation to find the height, and it ends up being about 13.09. So 13.09 meters. All right. And then, so that was part 8. And then for part 9, well, we've done this before. This is like launching something into a bucket. So we can do the same thing that you did in the lab. We know our initial position. In this case, we don't know our final horizontal position. Our horizontal velocities are the same at 28 meters per second because this is the same launch that we were just looking at. Horizontal acceleration is 0. And the time is not 0.49 seconds. That was how long it took to get to the hoop. Now we're talking about how long does it take to get to the pool, which should be about 2.17 meters off the ground. So we have to use our vertical quantities for that. His initial position is 6.71 meters. His final vertical position, 2.17 meters. His initial vertical velocity is 11.3 meters per second. We don't know how fast he's moving down. His acceleration is negative 10 meters per second squared, and the amount of time is unknown, but we can find it. We have enough information in the solver. So I'll put that in, 2.17 as our final y position. We don't know the final velocity. Trying to find time, we'll use the first equation, and we get, well, there's a negative. That would reflect a time that happened before the launch, so that's not what we're looking for. And then there's a positive time, which is 2.6 seconds. And if Mr. Brugger is moving for 2.6 seconds vertically, he was moving for 2.6 seconds horizontally. And now we can do that in the solver to determine how far horizontally he goes in that amount of time. And the answer ends up being, we're going to use the first equation again, 72.8 meters. So the answer to question 9 is 72.8. And so with this kind of a question, you can see there's a whole bunch of stuff that we can really think about. And this actually all very closely mirrors what we did with the lab, even the part about the initial perfectly horizontal velocity, because what we did with that is we just figured out the speed of the launcher, just like you use Tracker to find the speed of the launcher in the projectile motion lab.